Hello everyone. Today I just have a quick tip and trick for you for setting thermal contact resistance when you're analyzing conduction between two solids in Ansys Fluent. Thermal contact resistance arises because we never have perfectly flat and smooth materials. So when we take two materials, for example material A and material B, and we put them into contact, there's going to be small gaps and voids between that contact line. Those small gaps and voids can lead to a thermal contact resistance, which will change the temperature as we transition from our first material A into our second material B. If we want to do accurate simulations of conduction between two solids, we're going to have to account for the thermal contact resistance at this contact point. The thermal contact resistance value is going to be dependent on the two materials in contact, so material A and material B, as well as the contact pressure between those materials. If we look at the example on the right here, we can look at this problem in an electrical equivalent, and we can see that we have our thermal resistance as our temperature moves through our initial solid, which is going to be K2. As we hit the contact between K2 and K1, we're going to see our resistance from our thermal contact resistance. And as we move into K1, we're going to get our thermal resistance through our top solid. If we plot a temperature plot through the two materials, you can see what it will look like. We'll start with our high temperature on our top material. We're going to have a step change when we hit our thermal contact resistance, and then our new temperature through our second solid. In Ansys Fluent, thermal contact resistance is applied at a contact face between two solid materials. The parameters that we need to give Fluent to calculate the thermal contact resistance are going to be the wall thickness as well as the material selection. And there's two cases when you're calculating thermal contact resistance that you'll likely come across in your own simulations. These two cases are where you're given the thermal contact resistance between two materials. This is often found in a textbook or other reference material. So for example, in this case, where we may have copper in contact, we'll start with our equation for the thermal contact resistance, which is RC, or the thermal contact resistance, L1, which is the length of the material, K1, which is the thermal conductivity of the material that we'll give to Fluent, and then A, which is the area of the contact face. We can rearrange that equation to calculate L1, which we'll have to provide to Fluent. And in this case, we'll take RC as 5e-4 meters squared Kelvin per watt, which in the reference material is the thermal contact resistance between copper and copper at a contact pressure of about 100 kilonewtons per meter squared. We can then use the copper material and the thermal conductivity of copper, which is roughly 387.6 watts per meter squared Kelvin, as well as the area in contact. Plugging into our equation, we'll come up with an equivalent length value of about 1.211 e-4 meters. The other case is where we're given a material and a thickness of that material in between two solids. So for example, it's common when you're trying to get heat transfer between two solids to add a thermal paste or other thermal interface material between the two solids in contact to improve the thermal contact resistance. In this case, we're usually already given K1, which is the thermal conductivity of the material, as well as L1. So we won't have to calculate anything and we can put those directly into Fluent. But we can also go ahead and calculate what our expected thermal contact resistance will be by taking the length of that interface material, the thermal conductivity of that interface material, and the area in contact. Plugging into our equation for thermal contact resistance, we can see our expected thermal contact resistance value of about 0.2 meters squared Kelvin per watt, in this case using an off-the-shelf thermal interface material. So let's hop over into Fluent now, and I can show you what that looks like in your simulation. So now that we're over in Fluent, I've run a simple simulation where we have a chip which is producing 25 watts of energy and is about 5 meters in height. And on top of that, we've placed a heatsink, which has a 1 millimeter base, as well as an array of 10 millimeter pins. So we can see in this case, since we're generating heat in the bottom section and then dissipating heat with the heatsink on top, we have a contact layer between the heatsink and the chip below. capturing the thermal contact resistance between these two solids is going to be important to make sure we have an accurate answer. So in this current simulation that I ran, we do not have any thermal contact resistance. And if we plot the temperature profile between the center pin, we can see that we have a smooth transition from our hot base on the bottom. Our interface point is a smooth inflection point, and we move into our pins where we dissipate the thermal energy. We can now go ahead and implement our thermal contact resistance in two different ways. So what we're going to do is we're going to come up to the boundary conditions here. We're going to look for our contact, which we called out as a contact wall between the two solid materials. We'll double click on that. And what we'll be greeted with is our standard coupled wall condition. So now what we're going to want to do is we're going to want to implement our wall thickness as well as our material selection. And we previously calculated our equivalent wall thickness, which is going to be around 1.21125 E-4 meters. We'll go ahead and click on apply on that. And with our thermal contact resistance in place, we can go ahead and reinitialize and rerun our calculation. So now that we have rerun our calculation, we can see that we have a small step change between our hot chip below into our heatsink here. And if we go ahead and replot our temperature through our center pin, we can again see that we have our hot base. We have a small step change from the thermal contact resistance between those two solids in contact, and then the dissipation of the thermal energy in the upper heatsink. The second way that we can implement the thermal contact resistance is again going back to our contact wall condition. And instead of using copper, we're going to now implement our thermal interface material. So in this case, I went up to the materials tab. I created a new solid, which has the equivalent properties of our off-the-shelf thermal paste. We can then come back to our coupled wall condition. We can change the material selection from copper to our thermal paste material, and we can add in the expected thickness of our thermal paste material, which is going to be about 0.0005 meters or 500 micron. We'll go ahead and apply that and rerun the calculation and see how this looks. So now that our calculation is rerun, we can see that we get a much more dramatic effect with that thick layer of thermal paste in between these two materials. So we can see we have a very abrupt step change from our hot chip below into our heatsink. Again, if we plot the temperature through the center pin, we can see that very abrupt step change as we have our hot chip, our thermal interface material, which reduces our heat transfer fairly dramatically, and then our dissipation of the thermal energy in the heatsink. So that was just a quick tip on how to add thermal contact resistance into your simulations to try to increase the accuracy when you're looking at conduction between two solid materials. You can now go back and try to improve your system by either changing your contact resistance between two solid materials and improving the flatness or contact pressure, or again, scoping different thermal interface materials and seeing which one works best for your application. If you found this tip helpful, please like, share, and subscribe to the channel. Thank you.